We're here for Android, one route to own them all. Jeff Forrestal.
Thank you. Hello. So as I said, I'm Jeff Forrestal. I'm CTO of Bluebox. Bluebox is a mobile security company. So as it stands, it probably makes it relevant and why I'm talking about Android if I professionally am playing around with mobile devices these days. Some of you know me from a previous life where I dabbled in web stuff. For anyone who understands the reference, sorry I'm not wearing a shiny shirt. But for the most part, I definitely have a long history presenting here at Black Hat and many other places. So feedback survey, as was mentioned. Now, I hope I really don't need to give you a background on what is Android, because if you don't know by now, I mean, you're probably going to get something out of one of the other talks. So feel free to get up and leave if Android's not known to you. But otherwise, so essentially I'm going to cover Android. Now, actually, it's already been covered. If you've been kind of keeping tabs on the media for the last few weeks, there was some media reports coming out about this Android master key vulnerability. That is essentially the vulnerability that this talk originally targeted. Now, the tricky part of trying to keep 0-day under wraps until the point you get to Black Hat is that there's a 6-month lead time between when you know about the 0-day and when the talk happens, and you just sit there, cross your fingers, and hope that it doesn't leak in the meantime. This one leaked. It's been out for about the last 3 weeks. It has been using the title master key, but realistically there's more than one. And so today I'm actually going to cover a couple of them. They're all related. So essentially the multiple master keys, multiple patches, I do want to cover them all. So this talk content grew from the one bug I was originally going to cover about 4 bugs and all kinds of interesting things that have happened since then in the last few weeks. Now, for anyone who has actually read some of the technical disclosures and the material literally released in the last 2 weeks regarding these bugs, you may have already read some of the details of how these bugs work and stuff. So to a certain extent, the content of my presentation may be slightly redundant, but I really hope I'm going to wow you with awesome graphics and illustrations to make up for the fact that the content itself you may have already read. So the first thing I'm always asked is, how did all of this come to be? How did we find this bug? Which is kind of, an interesting story. So ultimately, I was sitting around with my Android team and, we kind of posed a self-challenge of, let's take a third-party application, go ahead and tweak the code in it, specifically like the GPS. We want to play around with the GPS API and return fake GPS coordinates. Have the app think we're in Antarctica or something. So that's all we want to sit around to do. So we grabbed the disassembler, reassembler. These are standard tools of the Android ecosystem. You can go look them up. They're fully documented. Disassembled the application, found where it's using the API, made the changes we need, reassembled it back up, signed it and ran it. It ran good. It got the right GPS data that we wanted, but Google Maps, the maps weren't showing up. And of course we're like, what the hell's going on? Where are the maps, right? We need maps. So we had to dig in. A little bit of reverse engineering later. The Google Maps API is licensed. That license that the app uses to talk to the Google Maps server is tied to the application signature, the developer of the application who signed it. So when we re-sign the application as part of changing the code, we change the developer signature. We don't have a license key under that developer account, so it all broke. So thus becomes the challenge of, okay, if we want Google Maps to work and do this, we got to find a way to change the code without changing the signature. And that's essentially what started off of this whole process to figure out how I can preserve a signature while still manipulating anything else I want. So, we did some reverse engineering ultimately. We had to figure out essentially from start to finish, from application install to the point in time where Google Maps API is consuming the signature for this license check. How do we get from start to finish, right? So applications, where do they query the signatures? They get them from the package manager service. So of course, where does package manager get them? Signature, the term signature is actually a misnomer. In Android space, what is the signature is actually the certificate, the public certificate of the signer. It's not the actual signature hash itself. It's just kind of confusion in naming. But ultimately, the public certificate used to sign the application is what essentially is returned by Packet Manager, because it's been stored in the system. So of course, where do those come from? Well, when you install an application, ultimately it goes through this application verification process, and assuming that the verification process is successful, then the certificate used as part of the verification process is basically stored in a database, and that's what's handed out for anyone on the device that asks for that app signature at that point. So, okay, well, through this verification process, how does that work? So you dig further, and ultimately you find there's essentially a class called Jar Verifier that goes and cryptographically verifies some signature, which is actually part of more of the Java jar signing spec. Right? Android just reuses Java jar signing for its own purposes, and that's essentially where this verification comes from. And we learned all of this essentially by cruising through and using the site androidxref.com, which is just a really great index of all the code online in web format with the web browser. You can point and click and search and basically walk through code from start to finish. It was a convenient tool. I use it all the time when digging through Android code bases. So ultimately, when going through the process, we really narrowed down exactly where this verification was happening. And the really relevant components in the Java space are the zip file class and the jar verifier class. And the tools that actually create these signatures, which are consumed by those entities, are the jar signer, the sign APK. And note that I kind of talk about, in one slide, APK, jar, and zip. Essentially, they're all the same. Jars and APKs are essentially zip files that contain very specific entries inside of them. But we're really just essentially dealing with different types of zip files. All right, well, if we're dealing with zip files, it reasons to believe we're going to have to dig into how zip works. So, quick overview on the zip file format. So essentially, the way the zip file is kind of constructed is that the the file bodies are kind of stored as individual local file records. And at the end, there's a big massive index called the central directory. And the central directory just has index pointers to those files with tons of metadata about the file. And that metadata includes things like the file name, and also includes pointers to where the actual file body contents live inside the file, elsewhere in the file. All kinds of other stuff like permissions and creation time and modification time, all this metadata goodness. Hello, someone's ringing. And so essentially what happens when a Java file or a Java application comes along and uses the zip file class, zip file enumerates everything in the central directory, loads it into a hash map, and basically it's just a bunch of zip entry objects where all that metadata is preserved and stuff. But essentially all the data is copied out of the zip file index, the central directory, and moved into another structure, a Java object structure, which kind of tracks all the entries. And all of that still maintains the metadata relationship as far as pointing back to where in the file all this stuff lives. So that when some Java application comes along and wants to process a zip file, it's essentially having the zip file class, open the file, create that object, then the application essentially just iterates over the entries or can directly request a specific entry as needed from that linked hash map. So pretty straightforward. Applications come along, this one class reads it, parses it, creates a big metadata structure blob of all the index items. Now applications can enumerate through and start using them. So let's swap over to that verification process. Now some of this is standard Java and then some of it starts getting into a little more Android specific. So essentially how the verification works, first round is all of the file bodies, each individual file is essentially hashed, and then there's a manifest MF file in the meta-inf directory of a Java jar or an APK, and essentially that contains the hash of all the individual file contents. So if you modify contents and they don't match the hash in the manifest, Java can detect that there's a modification there and warn you, and you can take action, whatever that definition means for the implementation. So now when we get into actual signed jars or signed APKs, another layer is added. There's a signature file. The name can vary depending upon what cert alias you use when you actually sign it. So the names will change, but the .sf extension will stay the same. It's called a signature file. Essentially, every entry in the signature file is a hash of all of the content for the same entry in the manifest file. So in a way, the signature file kind of hashes out the entries in the manifest file, and the manifest file is hashing out the body contents actually in the zip prior. Now that another layer happens, there's an additional file, it's a PKCS7 object. This is a signing object, standard PKCS type stuff, where there is a public certificate of who did the signing, and then a signature. The signature is a signed hash of the SF file. So if you kind of think of it, essentially what happens is there's a chain, right? The signed hash in the PKS7 object verifies the contents of the signature file. which proves the signature file is good. Then everything in the signature file, those hashes are checked against the entries in the manifest file, which proves the manifest is good. And then everything in the manifest, of course, hashes and checks the file contents and stuff individually. So through this way, you can essentially see there's a start to finish chain going from what is the PKCS signed object with the public certificate that is embedded there, all the way back to the file. It's pretty straightforward. Now it feels like there's a lot of layers here, but again, this is kind of how Java jar signing works, and so Android's just for the most part reusing it. Now you can go through and start playing, with this verification stuff. Essentially, if you add an extra file to the zip, so that means additional index entry and additional file body. When the verification process comes along, you get a discrepancy and it's ejected because the manifest and stuff in the manifest doesn't have a hash for the file that was added. And so when you try to install a zip that's been modified this way, you can kind of see possibly that error message. Basically, it gets kicked out as no certificates. And really, if you look in the details of Logcat, so like the Android debug log, and it says basically there's an extra file there, but it doesn't map up to this chain of assigned certificate, so abort the installation. So you can't do that trick. You can also try tricks where you're modifying the manifest without changing the properties of the zip file or without changing properties of the signature file. Those will all get detected and rejected. Basically, you'll get an error message that probably looks something like this, which is basically saying an invalid digest, right? Because again, all this hash and chain stuff is not correlating, it's detecting a discrepancy, so it's aborting the install. So you can do the same thing with a signature file. If you make any changes to the signature file itself without the other stuff, it will be detected and the installation will get aborted. And if you start manipulating the public certificates and the actual signature hash in the PKCS7 object, it'll also get detected and aborted. Short of actually just completely changing the public certificate and re-signing from scratch, but at that point, you are no longer using the original cert, you're not the original developer, you just became a new developer for the same app. And that's allowed, but it's essentially a new app as far as Android is concerned at that point. Now I went through and actually manually tried a lot of these tests because it just seemed like fun. What happens if, and tried all these. So in the process of trying all this kind of stuff and playing with the Java verifier and what it does detect and what it doesn't detect, I found out that I did something and I got a successful installation and it didn't puke out on me, which was kind of surprising. So that situation was I put 2 copies of the same file into the zip file, which is kind of hard to do with command line tools. You have to do a little bit of binary editing. It's not hard. I'll show you a trick to do it later. But essentially, and then this is not malicious. This is just 2 legitimate copies of the same file. In this case, I use the classes.dex, which is the file where essentially Android applications store all of their Java Dalvik bytecode, right? It's like the main core executable code for the application, all stored in that file. 2 copies. I installed it. It was successful. It accepted it. The app ran, no big deal. So I'm like, okay. It seems to not care if there's duplicate entries. So let's start playing with this. So I custom created then an application where I put 2 classes.dex. Now rather than the same ones, the first one I put the original code unmodified. So that's the green good copy. And then I put my modified maps code, because remember I'm still playing with that same application where I wanted maps to work. So I put our modified code as the second entry. So they're both called classes.dex, 2 entries. The first one's the good code, the second one's the bad code. So kind of ran it, signed it, verified it. Jar Signer seemed to be happy with it, but when I actually tried to install it into Android, it completely puked out and got rejected. So I'm like, okay, that trick didn't work. But on a whim, I decided, okay, but it got rejected because it verified the contents, they don't seem to match. So let me swap the order. Let me go ahead and make a zip file that has the modified bad code in the index first, and the legitimate code second in that linear order, and give it a shot. So of course I go through the signing and verification process. Jar Signer's not happy. When I go to actually install it into Android, boom. And what does that mean? I got my maps. I'm a pretty happy dude at that point. But of course I'm like, I got my maps, we did our little, party dance, we solved this problem, so that's all we wanted to do. But then we started thinking, all right, we started settling down. It's like, wait a minute, I'm pretty sure we probably just did something we're not supposed to do, right? And so now it's like, all right, what do we got here? We got to go back and now do the post-mortem of exactly what the heck just happened. So essentially, where did this bug come from? That's the process of how we came across it. And to a certain extent, it was a combination of white box, black box, all manual, a little bit of trial and error, and quite frankly, a big pile of luck as well. But certainly we were tactically aiming based on code reviews and stuff that we're manually doing too. So it was an informed kind of debugging session and trial and error session. But really kind of looking back at what was the core problem when I went through this process, the actual root cause of the problem for this bug is the use of a linked hash map object in JavaSpace. Why is that? Well, let's think, kind of going through the concept of how a linked hash map works. When all those entries are loaded essentially in, a linked hash map has an interesting property where it doesn't allow duplicates. And the later one overwrites the former one. So as long as all the entries are individual and not duplicated, all of them are loaded in, everything looks good. And even that first load of the classes.dex, the evil one, loads an entry that points to the evil code. But then when the second one is encountered, it updates the hash map with new metadata for the second entry, but it overwrites, since the key is the file name and the file name stayed the same, it overwrites the previous one. So you can kind of see here illustrated how the hash map now contains, for the class's dex, the pointer to the good one, and we kind of now just lost that pointer to the bad one. And so when jar verifier comes along, it enumerates all those entries, it follows those pointers to the file contents, verifies the hash bodies, it's happy. And it should be, right? Because all the files pointed to are all clean. So the question is, where does this evil copy come into play? Well, so we got to go see now this is outside the verification process. We have to see what happens after the verification process. Well, things are handed off to package manager, who starts doing the package installation process, because it's verified. As soon as verified's clean, then the whole install process starts. So what winds up happening is package manager hands it off to installD, the installation daemon, and installD hands it off to a program called dexstop, which is really the program responsible for extracting the code and optimizing it and getting it installed onto the system ready for execution. Now what's interesting about dexstop, it's not written in Java, it's written in C. And it winds up having its own zip file parsing implementation that's completely separate from the Java one. It's written in a C code. It's called zip archive, and it uses a hash list. Now the interesting thing about the zip file hash list in the C++ code is that it allows duplicate entries and it preserves insertion order, which basically means when it goes through and reads all those entries and starts populating that hash list with the metadata, it is going to put two entries. And they are going to be exactly in the same order as it encountered them out of the central directory. And then when dexstop comes along and says, please give me the class's dext file, it's going to go through and it's going to wind up hitting and matching the first one and always returning the first one. So unlike the Java implementation where the second one overwrote the first one and the verifier used the second entry, in this case the actual installation application gets the first one and installs the first entry. And that ultimately what winds up in the discrepancy, right? So it all comes down to a discrepancy of zip file parsing. Did I use the first one? Did I use the last one? And the differences thereof. Now there's, I just want to point out, because it's partially relevant, there's a different actual component entirely which handles a different file inside the Android app. The Android manifest goes through the asset manager. It has a different implementation of zip, also written in C++. Its behavior is largely the same as a dexstop one. Same thing, preserves the insertion order, no duplicates, or allows duplicates. So it has the same problem, but it's interesting that it's a different component with a third zip implementation that has kind of the same discrepancy. And actually Sorek's done a great analysis and scrubbed the code base of Android. He basically found 8 separate zip file parsing implementations present in the Android code base. So if you think about it, this is a discrepancy of using one for security verification and using one for actual use. We've got 8 of these things floating around. Depending on which one you use at what time, you may or may not be vulnerable. And that's really where all of this, that's the root cause of this whole problem. So now that we kind of understand what's going on, great. I just got myself some some maps on a Foursquare app. It seems to me that maybe we can take this a little bit farther, beyond some third-party little manipulation of some Google Maps API. So let's briefly cover a couple relevant items of the Android security model. So essentially, applications, when they're first installed, are put into an application sandbox. So when fresh app, never seen before, right? Android will assign a Unix user ID, so a UID, standard Unix stuff, and kind of create a sandbox. And that app will forevermore basically be exclusively assigned that UID. There's some things with some shared UIDs and stuff which I'll get into in a second. But essentially, overall, it's a container for that app, it's a sandbox for that app. The only way to get into that sandbox is to be by the same developer. And how that's basically proven to an Android system is be signed by the same certificate. And this is actually how updates work, right? So if you install, for instance, Gmail, it'd be uncool now after Gmail is installed and there's email data in the Gmail app client, if some arbitrary app came along and tried to do an update to Gmail, jumped in its sandbox and grabbed all your email, right? So the only way that Google can issue a Gmail update is because it's signed with the same certificate as the original Gmail installation. So the sandbox is created initially, signed by Google, and now an update to Gmail is also signed by Google. Since they're both signed by Google, the update's allowed to go in the sandbox and change all the code and still access all the same data. If it was not signed by Google, it would either get rejected because it's considered not to be by the same developer and contrary to the security model. If you change the package name all you want, you can make it, Gmail X Foo, and it'll just get installed, but it's essentially a separate app at that point. But ultimately, you can kind of see how essentially certificates are the key to getting into sandboxes. Now, the system itself, as a whole, the Android operating system, I'm hesitant to call it operating system because I'm not including the kernel here, but essentially the Android operating system itself subscribes to the same notion of a sandbox. There's a system sandbox, which is a misnomer because it's not really a sandbox. There's no boundaries. This is the sandbox that enforces all the other sandboxes, right? And essentially, any application can actually request access into a sandbox by name, right? In this case, Android UID system, an app can come along and say, I want to be a part of the system sandbox. I want to be an OS extension, please. And as long as it is signed with the platform certificates. Now, the person who produced the firmware, which is typically the device vendor, but if you're using kind of like CyanogenMod or aftermarket firmware updates, it may be someone else, but essentially whoever produced the firmware of your device signed all of those base firmware components with the platform certificate. Normally this would be like Samsung, HTC, Motorola's key, right? That actually produced the device. And so now if Samsung, HTC, or Motorola want to release a system update, all they have to do is create an app, sign it with the same platform cert for that device, and request system UID access, and that thing essentially gets loaded in and is granted system level access and essentially becomes part of the operating system. So it's like the ultimate sandbox, it's the ultimate goal in terms of the security model. So of course, I keep talking about system, and I'm specifically not saying root for a reason. If you look at kind of like the software privilege stack, certainly the kernel is the king, and then you got your typical root after that, and then comes system, and then everything else below it, where eventually we bottom out with normal applications beneath that. All the things in the middle are essentially kind of like some identified different privilege levels for specific circumstances and permissions you would grant to an app. But by the most part, you can kind of see where system fits in the grand scheme of things. Now, system's not root, but let's really take a moment to think about what system does, right? So system manages, installs all of your applications and makes sure they're all acting properly, and kind of even facilitates sandboxing. Because it manages all of your applications, it essentially manages all the data used by those applications. It can go in and jump in and have access to it. Now there are a couple proprietary technologies recently on the market that kind of start to change this, but by and large, this is a general statement. Since it's actually managing all your accounts and everything, your PIN code, your lock code, all that stuff, it's essentially managing your passwords. The Android key store is owned and run by System. That's where you stash all your passwords. So System has access to all of your security credentials. And of course, since it is a thing that actually implements and enforces and uses all the configurations of your device, by and large, it does control all of your settings. So System's not root, but at the same time, it has all of your data, it has all of your apps, it has all of your passwords, it has all of your settings. Other than jailbreaking up to get root and maybe playing around with a kernel module too, what's left? Right? So system in its own right is actually a pretty powerful stopping point to get access to the majority of the device. So I'm thinking, all right, knowing this shared UID system thing and knowing this platform certificate thing, essentially if I use this cute little trick where I can change code without changing the certificate, all I really need to do is get my hands on an app that is platform signed, so signed by the same person who produced the firmware for the device, and do my little trick on it, and theoretically, I should be able to get system level access. Much cooler than Foursquare Maps, right? Although Foursquare Maps is a very powerful thing in its own right. So, the challenge is then, okay, what apps basically meet that criteria? And this is where some of my work elsewhere in Blue Box actually kind of gave me a hint, because for anyone who's kind of dealt with the MDM management space and kind of looked around there, there's a lot of interesting B2B relationships between like MDM vendors and device components vendors, aftermarket device component and vendors, and manufacturers. For instance, the Samsung Seat program is a great example. Samsung has a really fantastic platform management API that they offer to partners. So if you become a partner of the Seat program, you can have access to the API. The challenge is that API actually needs platform level certificate access. So the only one who can really give away API access is Samsung. So as part of the SEEP access, partners are able to produce an application which then they hand to Samsung. They verify it cleanly and make sure it's not malicious and it's contained and it looks really good. So they verify it, and if they're satisfied, Samsung will sign it with their platform certificate and give it back to you, and you upload it to Google Play. So in that case, really, essentially, to use Samsung's extended API, you have to be platform signed, and there is an entire B2B relationship process to produce this. Samsung's not the only one. LG does this. HTC has access to a lot of the extended API, but certainly there's other opportunities. For instance, with VPN add-on vendors, Cisco, Juniper, F5. These guys want to do VPN client access on the device, which is something a normal application can't do in the privilege model of Android at all. So, as an example, Cisco has relationships with HTC and with Samsung, who Cisco creates their basically their VPN client, but it needs system level access to do its thing, affect routing tables, play with the TUN interface, stuff like that. So they've got relationships with Samsung, with HTC. Cisco has produced the client, given it to those parties. HTC signed it and given it back, and that's what's hanging in the App Store right now. So when you go for that HTC AnyConnect, that's actually signed by HTC. You go to the Samsung AnyConnect, it's signed by Samsung. If you don't have signed, platform access, you can go to, the rooted one. If you look around, what I typically do is I just go into the Play Store and kind of search for ZTE, for Samsung, for whatever, and you'll be amazed at how many apps pop up. Get rid of all the themes and stuff, and what's left tends to be a lot of MDM platform management extensions. And if you start looking under the hood and verifying those, you'll see they're not signed by who created the app, they're signed by the platform device vendor. And so in this case, I grabbed the Cisco one and started dumping it. Apologies if that's hard to read, but essentially I can look at that PKCS7 object, dump the certificate, and actually see in the Samsung AnyConnect client produced by Cisco, it's actually signed by Samsung. And as a complete bonus to make my life easier, it just so happens that the VPN clients like Samsung, Juniper, F5, all these guys who produce these things this way, actually requests system UID access. And now, of course, it's up to Samsung's discretion or HTC's discretion, the platform vendor's discretion to hand it away, and they do so under whatever contractual agreement they've got, like with the Cisco, Junipers, F5s of the world and stuff. But ultimately, I just grab this thing. It's platform signed, and it's already requesting system level access. This is pretty easy. I mean, the criteria is met at this point. So what do I wind up doing? How do we exploit this? Well, I take this uber hacking tool called Eclipse. I do this awesome code craziness called create a Java project. And the secret key is I just use the same package name as the original app, right? So ultimately, I just basically make a package saying I'm going to be Cisco AnyConnect VPN Android. That's my package name, right? And so inside of that, I go through and ultimately, I have to look at the original app and say there's so many entry points, I only need to grab one of them and take over one of them. So which entry point do I want to choose from? It could be an activity, it could be a service, it could be a content provider, your call, right? Ultimately, I wound up just picking the main launcher activity, and I created just a package. I created an empty activity that used the exact same class name as the one that's embedded in the original target app, in this case the Cisco VPN client, and just dropped my code in it. And I had to create a couple other small files, and this was through trial and error, trying to do this process, launch it, and then I would get a failure saying can't load file X. Well, I'll make an empty version of file X, try again. I only had to do that twice until the thing worked. So realistically, I just created basically a modified Cisco representation of the code base, not copying code, not reusing anything. All I did was just create a completely empty from scratch new one with 3 empty files in it. And that's all I need to get started. Now in that activity, let's look at a payload, right? Let's exploit this thing. I don't care about good design practices when you want to get a POC to work and it's late and whatever and you're fueled by adrenaline, you just do what you need to do to get it done. right? So I'm like, every time an activity is created for the first time, the onCreate's call, good enough for me, I'm gonna slap my code in there. That way I guarantee it runs. None of this activity life cycle stuff that a good developer would normally worry about. So I just throw the code right there in the onCreates. And if you can read it here, essentially all I'm doing with this payload is I'm shelling out and running the ID command, which will essentially tell me what user privilege I'm running at, and then just reading in the results of that command and dumping them into the log file, the Android debug log. So straightforward payload, that's the entire thing. This is it. This is the whole exploit body. So of course, now that I've got a payload, I compile it with Eclipse. Now I've got to do that silly little zip stuff, right? And get all the bodies in the right order. There's been some interesting POCs released that do like crazy Java and Python and do this and merge APKs and all this assorted stuff. And as kind of other folks like Sorek have kind of pointed out and stuff, I mean, realistically, a lot of people are overthinking it. All I got to do is take the original target application, take my modified classes dex file, and update the existing one in the app. Then I take the original class's dex, it's renamed to classes DEY or whatever else. I append that to the end. So now the zip's got two copies. The evil one is first, and since I appended the second one comes later. The second one has the wrong name, and then I just do a binary edit, in which case it could be a sed command, to swap the name of the second one back to the original name I need it to be. So even though the zip commands won't let me do duplicate files, directly, I can still use zip commands to completely manage the entire process. Just use a slightly different name, and then just briefly binary edit the name back to where it needs to be. Boom, done. 3 commands, exploit, lock, and loaded. So, of course we run it. A course is successfully taken by Android, and then, I dump the log output, and there you go, boom. UID 1000, system. The entire process works as suspected. So, we've got system level access. Straightforward, awesome hacker Eclipse tool. Wrote some Java code, got myself a part of the Android OS. Fairly straightforward to a certain extent, definitely accessible. Not too complicated, right? There's more fun stuff. Unfortunately, so to a certain extent there's more fun stuff, but I think this is probably the point where people are going to get disappointed. So we got system. Let's keep going, right? Chasing root. So certainly the challenge with chasing root from system level access, while there's definitely a lot of system to root type of escalations out there, they do vary by manufacturer, they do vary by Android version and stuff. They really start to get splintered. You can look at places like XDA forums and stuff to kind of see what's the latest exploit to get from system to root and just kind of throw that in your payload and call it good. For an older version of Android, just an example, there was something called the emulator hack for Ice Cream Sandwich. Essentially all you had to do is there was one file called data local prop, which is normally not writable by normal applications, but with system you can write it. So as system we open that file, and inside of it we basically set a property saying I'm running in an emulator, which the code in Android that's even shipped on production devices generally has this, if you're running in an emulator, you're in development mode, feel free to skip all this security crap and just drop into root, right? And devices actually ship with this because normally, obviously you're not running in an emulator. A normal device will not set this flag to indicate it's running in an emulator. It's a production device, so all the security properties and controls will be maintained. But if you set this flag and reboot, through this thing, now that we have system level access, we're at a place where we can set this flag, we reboot the phone, we log in, we got root, right? Simply by tricking the device into thinking that it's running in an emulator. Now this hack actually, to a certain extent has been closed in 2 ways. One, Android no longer will actually read that file. The kind of fun quote mentioned external is that the only thing that data local prop file was ever used was actually for exploits. It was never legitimately used by anything for real. So it's no longer even processed anymore. And I've also seen some other vendors who literally go in on their production devices and in the ROM properties that get loaded first specifically say, I am not in an emulator. So and it's a read-only variable, so once it's set as I'm not in an emulator, you can never change it to say I am. So, multiple ways to kind of mitigate it depending upon the direction and stuff, but certainly that trick has been rendered useless. But come on, you don't want stuff that doesn't work, you want stuff that works. So I want to point out, the awesome effort done by Sorek. Recently, he released a tool called Cydia Impactor, which was kind of billed as the end-to-end MasterKey exploit management suite. This is essentially a fully automated suite for OS X or for Windows. It's point and click. right? You connect a device, you point and click, it figures out the app, it builds all this stuff, it constructs it, it delivers it, it pops system level access, it starts running system to root level escalations, whatever the latest ones are being maintained, and if you get it, you get it, if you're not, you're not. Cross-device, pretty agnostic, fantastic work, quite frankly. I was gonna release some cheesy little POCs for a couple big vendors, then this came out and I said, what's the point for my crap? This thing is point and click and has UIs and awesomeness. I mean, I can't compete with that. And it's maintained and all that sort of stuff. So I certainly encourage you to go check it out. So what's really interesting about this bug, I was kind of actually hearkening this back to the ancient days of like the IIS MSADC exploit and stuff. I really like this bug because it doesn't matter what architecture you're running on. All those silly little security things like ASLR and DEP don't apply here. It works, I have one exploit payload that works on 4 generations of Android with 0 code modifications. That itself is pretty cool. And I don't have to be an assembly expert and do crazy payload shellcode and stuff. If I can write Java, I'm game on, right? So this is a really easy one, ultimately, to get your hands around and kind of exploit. 3 zip commands or 3 command line commands to kind of produce it, and boom, you're done. You write some Java code, you're set. So in that regard, and that's actually why I wanted to bring it or kind of submit it to the CFP for Black Hat, because it was an easy to understand, easy to exploit, easy to just really get your brain around. This is a really simple, easy, accessible vulnerability. Now, of course, if it's easy and accessible, that, you kind of have to look and say, okay, what happens now when people start using it? So before we go into, some other interesting tidbits, remember I said master keys, plural. As it's come to light recently, publicly known, and certainly from some private responsible disclosure efforts, there are other bugs that are really playing in the same space. And depending upon how carefully you go and watch AOSP patch releases and things like that, you may have noticed a couple more. And certainly the public has. And so it's relevant for, I'm gonna go ahead and throw them in since I've already given you all the foundation of all this zip file stuff. I taught you more zip than you're ever gonna wanna know, so let's use that to have more fun, right? So there was one patch that was released that had to do with authenticated attributes. This is one interesting enough that has the same impact, but it hasn't been, the patch is out. It's publicly in AOSP, yet no one's actually called attention to it to actually producing the same impact as all the other master keys. So this is a snippet of code that is right smack dab in the middle of all that RSA certificate crypto signing verification process. Does anyone see anything that's probably not cool to have right in the middle of your RSA cryptographic signing verification process? I know it's hard to read, but essentially the to do, we should figure out what to do here part is probably a huge miss, right? I noticed this now, to be completely fair and stuff, Blue Box noticed this. I was kind of slacking on making a POC and stuff. I did not report this to Google before they wound up releasing the patch in AOSP because they've been internally scrubbing for these whole code paths and stuff after the first master key came out. So it was not, Blue Box is not going to claim we found this, but certainly we were playing for it, but ultimately it got fixed before we actually got involved. So, but I still want to talk about it anyway because it's interesting and I happen to do the work to understand it, so figure why not include it. So if you remember back into that verification process and that chain, right, that whole verification chain, all these authenticated attributes do is they add one more link to the chain at the end. So rather than the signature hash in the RSA file verifying the signature file, what it does is now the signed hash verifies the authenticated attributes. Inside the authenticated attributes, there's a hash of the signature file, right? So you can kind of see how we just added one more link to the chain, ultimately sign the auth attributes. The auth attributes are actually what verifies the SF verifies the MF verifies the byte contents. Now due to that to-do little missing blip, we're missing a link in the chain. So essentially the signed hash will verify the authenticated attributes, but the to-do missing part was making sure that the authenticated attributes verify the signature file and continue down the chain. So from an exploitation perspective, ultimately all you have to do is just basically make your modified file, update your manifest, update your signature file, and it's completely fine because any changes done to any of that other stuff to the left won't affect the authentication of the attributes on the right, and then the link in the chain isn't actually correlated so that that discrepancy isn't detected. So what really winds up happening now, to be fair, quite frankly, while this looks interesting, exploitation to this is practically going to be near zero. And the reason is because you need an application signed with authenticated attributes as your starting point. Very few applications, now it is a legitimately supported signing method, but if you look at like SignAPK and JAR Signer, the actual tools in the ecosystem to do the signing, they largely don't produce signed applications this way, which is a good thing, right? Because that really means most applications will be safe from this. That said, if someone did actually produce a signature, a signing this way, what you can essentially do is copy and paste that RSA file into any other app you want, and that app will essentially assume the identity of that developer. Because you're essentially just copying and pasting that right half, and the left half is irrelevant. It'll just assume the identity verified out of that right half. So it's kind of, you know, for the most part, anyone who's signed with authenticated attributes is essentially giving away their identity. And they should probably go revoke all that stuff and kind of, you know, fix up that process. Fun, cute thing, not practical to really exploit, but I thought I'd mention it. A much more interesting patch that publicly showed up. You know, so again, this one, Blue Box did have some disclosure hand in, and some stuff started happening really fast on this one publicly before responsible disclosure really played out the way it would normally play out, but that's just how those things go. So essentially, remember we're talking about differences between a C++ zip parser and a Java zip parser, right? So all of this is about a discrepancy game. The Java one doing one thing and the C++ doing another, and if we can prey on discrepancies, we can completely break that verification process. So as it turns out, the C++ implementation used by Desktop and others, like Asset Manager, things like that, use unsigned short values, whereas the Java implementation uses signed short values. Now, for those of you briefly not aware of the difference between signed and unsigned, if you think about numbers represented by a computer, they can be positive, they can be negative. Signed means that 2 bytes, in this case for short, will represent somewhere between negative 32K and positive 32K if it's signed. If it's an unsigned integer, unsigned short, it'll represent a value between 0 and 64K. So there's a certain crossing point in those values here, hex 8000, where essentially interpreted as a signed value, hex 8000 means negative 32K. Interpreted in an unsigned way, hex 8000 means positive 32K. So the same number means a drastic difference in negative and positive depending upon who interprets it. So when you look at what happens, if we essentially use that magic number of hex 8000, the C++ implementation, which treats it as unsigned, will add it to a pointer and it's going to jump 32K forward, right? It's going to move through the file when it's parsing it, jump farther 32K. When you look at what zip is doing, or the jar implementation of zip file, since it's coming out as negative 32K, then it's doing that check of if it's greater than 0, which negative 32K is not, it essentially doesn't advance the pointer at all. So what winds up happening is that the C++ implementation is jumping 32K ahead, and the Java implementation is just going to the next record. Big difference on what comes next, right? So we can exploit that. And so essentially if we basically, again, go back to these funky kind of ordered, unordered things, we create ourselves one of those funky indexes, the central directory, and in it I wind up putting a file that has that magical 8000 hex, so normal file X, normal file Y, normal file Z, but I update the little jump pointer with that magic value of 8000 hex, right? And then after that, right after it, I put an entry for the good unmodified code, and then specially carefully crafted 32K offset kind of, you know, with some padding and stuff. I put another evil entry which points to the modified code. And then I could put additional files after that and, you know, or end of central directory, whatever it matters. But I create that basically these two record items. So what winds up happening is the Java one comes along and reads, says, okay, file X, that's good, file Y, that's good, file Z, that's good, oh, negative, jump to the next one. It gets our original class's dex, right? And remember, and it's going to all verify all the file bodies look good, so it's going to get the real one and it's going to be happy with it. And then of course it's going to jump farther forward. It's going to jump over the evil one because I put some additional jumps in there which are not negative sensitive, causing it to jump anyway, artificially, and it just goes to the end. Versus the C++ one, when it comes along, it's going to, again, get X, get Y, it's going to get Z with that funky value. That funky value says jump ahead 32K, so it's going to do the jump, and at 32K later is exactly where we put our evil one. And that's the one that the C++ implementation is going to get. And then eventually they start coming back into sync as they start processing the next record. So again, that discrepancy shows that, you know, that I gave one file entry to one implementation of zip, the one that actually does all the security checking, and then I actually gave another file entry to a different implementation of zip, which is the one that actually installs the code and uses it. Now, as correctly pointed out through like a great technical analysis of Sork and stuff, who kind of really dug into this bug and posted a big blog post on it, that it's not just about even replacing one file. You can use this trick to literally feed an entirely independent copy of a new zip file to one implementation versus another. So you don't have, this isn't even about one single file. I could put 30 files in one perspective of the zip and 30 different ones in a different perspective of the zip that have nothing to do with each other and feed completely independent sets of files in both directions. One to the one that does the security verification, and then one to the one who actually processes and uses the data actually in the runtime. So it's pretty powerful. You can invent files that don't even exist. They don't even have to match at that point, right? I can add files in one place that aren't on the other side. It's pretty flexible. And to a certain extent, I happen to know a couple little tricks and tidbits in this space that may be surfacing, eventually that will show even more power to this approach. This is a pretty powerful capability in terms of the ramifications, and you can do a lot of interesting stuff with this. All related to, signature bypass verification. So also related actually in the same patch, because that patch fixed multiple points in code. And so that the previous slide actually showed what amounts to 2 variations, because you can do sign and unsign in comments and sign and unsign in extra data. There was a third one, and this one actually showed up publicly released by the Android security team in a blog at blog Sinacom.cn in China. And so there's this awesome kind of technical analysis blog post. It's written in Chinese, so you'll have to Google Translate or know how to read Chinese to begin with. They even have graphics and stuff too, showing exactly how they construct the payload. And essentially what they wound up doing is, rather than playing around in the central directory and putting multiple entries there, they left it as a single entry in the central directory. What they targeted instead was actually the local file body content itself has a header. It has that same concept of an extra jump. And so they flopped that little signed trick over in the local file part. And so what happened is when the zip entry Java came along, again, it did a 0 advance, so it got the first copy of the file, here shown as the original copy. But when the C++ came along, again, it did that jump. So it jumped over the original copy and wound up landing on an evil copy, and that's the one it got. So essentially they did the same trick, they just did it in a different location. Now the challenge though with this one is, because they're jumping over file body contents themselves, and the jump can only be up to 64K big, that means this trick only works if the file's under 64K big. So somewhat limiting of the trick. The other way is much more powerful because you have unlimited body content size. But interesting nonetheless. And it's actually the exact same bug, just in a different location. So that kind of wraps up some of the recently disclosed, and I'll emphasize publicly disclosed part of the bugs kind of in this space. But in the last 2 weeks, quite frankly, it's been really interesting. And I want to kind of take a brief gander back at the timeline of how life looked. So, Blue Box kind of, encountered this and stuff, and ultimately in late February, we wound up, disclosing this to Google under the concept of responsible disclosure, and, kind of working with Google and stuff. And basically at the beginning of March, Google went ahead and released this patch to partners, all the Open Handset Alliance. And so life was boring. We relatively sat around, played with this bug in our own stuff, and that was it. Around June, device manufacturers started to actually release updates. We started actually seeing patches go out for devices. Samsung was the first one I personally saw issue an update, and I will actually give props to Samsung. They actually issued an update to fix this bug on an old Gingerbread 235 Samsung Stratosphere device. So this is, to a certain extent, props for the fact that they didn't go after and fix only their newer stuff. They went back to the really old Gingerbread stuff and released patches for that too, which is pretty darn cool, because typically people feel that only the new stuff gets the updates. In this case, not the case. So then, come July 3rd, Blue Box wound up releasing kind of like a teaser to promote this talk, to gain some interest, to hopefully get you guys here in the room. And a lot of media fanfare started happening. It took about 72 hours, and then quite frankly, right after all that stuff, just all hell broke loose. So in the definition of what all hell broke loose means, let's dig in. Now I realize this might be a little short, but there are some really interesting things if you look at timelines here. So briefly, we released the teaser. Around the teaser time, other patches, the other patches for the other bugs were surfacing, right? There's a lot of media coverage, and then ultimately, one way or another, there was a public open source project that got their hands on that patch that was circled around to Google partners, and they posted it into their public repo. As soon as it went public, it took about a day. Ultimately, the first exploit using that kind of patch to figure out how it works was eventually released. After that, we started seeing Blue Box released a free security scanner, actually telling people if they're patched for the bug. Since now it's out, we want to at least inform people to help them manage and understand the risk. So we released a free scanner that essentially tells you your patch status and actually tries to at least look through what apps you got installed and see if any of them contain this exploit for this bug. It actually parses the zip files and looks for the signed and unsigned, all that assorted stuff, right? And then around that time is when that additional blog post came out about an additional method for the other patch. Then Impactor showed up and really automated point and clicked everything. Samsung started finding malware, right? The first instances of malware using this vulnerability started popping up in the wild. Eventually the original one went out, and then other analyses and stuff showed up. Now the interesting things to call out from a timeline perspective. Now, July 6th was essentially when the patch went public. And for that most part, details of the bug were fully public. Took 1 day from patch details public to first working POC exploit, right? It took 15 days for it to be fully automated in a multi-platform UI, multi-device agnostic, awesome, complete thing, right? Now that said, it's tough to say, ultimately if anyone knew ahead of time and ultimately kind of had advance notice because they figured out the bug. So I'm only basing it upon the speculation of the public release date, right? And again, continuing on that, from the date of public details release to the day we first saw malware was 17 days. How does that sound for your incident response turnaround time? Is anyone working with that time frame from when bugs show up to when bugs are exploited in the wild? 17 days reasonable for most people to respond and get up to snuff? Now again, data public details doesn't necessarily mean the malware guys didn't figure it out ahead of time and kind of working on it prior to July 6th. We don't know. But I thought it was interesting. If it really was, if the clock started at the point of full public release, details release, 17 days turnaround time for malware in the wild. And just another interesting aside, it took about 7 days for people to start noticing that there were other master key bugs in AOSP patches sitting around there. From the time that they were kind of showing up to the time that actually someone said, hey, wait a minute, there's another bug over here that looks and works just like this original one. Right? So a week to kind of comb through AOSP. Now granted, people were looking because they were looking for that original patch. So it was getting much more attention than normal. Right? But they still missed that the third one that I discussed with the authenticated attribute. So it really depends upon what they were looking for. So another interesting kind of tidbit that I want to kind of throw out to the crowd, right? There was a lot of kind of, everyone's going to die because of this bug. That was essentially, I think, the summary of most media coverage. So not realistically. I mean, it was really kind of how many end users are going to be affected. Are end users really going to be hit by this? Is this an end user problem, or is this just kind of a really awesome jailbreak opportunity, right? So certainly, it's no doubt a really awesome jailbreak opportunity, and that's ultimately what we kind of position it as, but it kind of turned into this media storm of what's the end user risk. Right? And then this concept came about as long as end users are only going to Google Play, life is good. Don't get your apps from untrusted sources. And then strange quotes started happening as everyone knows that no user changes the allow untrusted sources setting on their device to allow any applications to be installed from anywhere other than Google. Right? It's apparently common knowledge. I was late to that party. I'm like, where's this data? Where's this statistic? Why does everyone but me know this? And so if you look at kind of the media, if you look at quotes in some of the circles and some of these conversations I was having that were publicly reviewable, a lot of people were essentially saying it's statistically near zero, the number of users who are essentially changing the security setting to allow themselves to be affected by untrusted sources. They all only go to Google. I'm like, okay. So when we released our Blue Box security scanner, it actually has the capability of sending us some anonymous scan telemetry data. It's completely anonymous. I can't even geolocate what geographic region the stuff is coming from. All anonymous, and essentially just tells us, are things being encountered in the wild? That we would like to know that if bugs are starting to show up. And it happened to tell us basically the security setting. So anonymous sampling set, of about 250,000 devices, we got some feedback data on how many actually changed the setting, or what was the status of the setting. Do they allow untrusted sources, or do they leave it as only Google Play by default, which comes by default? And the media speculation, the expert opinion is that users will not go through all these security settings, menus, and ultimately find that checkbox to uncheck that box to open themselves to the opportunity. So a quick poll of the crowd. I kind of narrowed it down to one of 4 choices. Which bucket ultimately do you feel, and again, based on 250,000 devices, which isn't a huge sampling set, but it's the only data I got nonetheless, which bucket do you think ultimately it is? Now, if you side with the expert opinion and all the Android enthusiasts and everything reported in the media, essentially the number's near 0. But what do you think? I'll give you 2 seconds to think about it. So if you said 69%, you are right. 69% of people, we'll invert it, 31% of people were secure. 69% of people at some point were not. And essentially what wound up happening is, so 31% basically only allow Google Play installs. These are the people who had nothing to worry about. And the other 69%, which I think statistically rounds to 0, I think, right? Have a problem on their hand. This number is a lot bigger than what that. And I'll be perfectly honest, I feel this number is high, and that's kind of part of what is really truly our sampling population. We can't geographically correlate if it was kind of aggregated into one area or another because it's truly anonymous. So I kind of had to look at Google Play market and when the little pie graph it shows me, and it was kind of all around the world, a little here, a little there and stuff, but I can't attest to truly what composed the 250,000 devices. So I would love to see this data on a scale more like 10 million, 100 million. But that said, it was still, even if this number was closer to 20%, this is still big. This says this is a bigger problem than even all of those Android experts think is. And of course, why? I want to point out, actually, because we get the scan telemetry data when they rescan, 3% of those people started with it unchecked, and then later on came back and scanned, and they had checked the box. So I can, to a certain extent, I can claim 3% of our users were informed that they had an insecure setting problem and actually changed the setting back. Hey, 3% is a small win, but it's a win nonetheless. All right? And then 4% were just dudes changing the thing back and forth, I think just seeing if the scanner did something, right? I mean, they're just, it was on, it was off, it was on, it was off, whatever. But the thing is, why are so many, why is that number high? It may not even be higher than 69%, but it's definitely higher than 0. Hopefully we can all agree to that. Why is it so high? And then start looking at what are the causes that cause users ultimately to want to change that setting. Well, there are a lot of motivating reasons out there, not just pirating applications, right? I mean, let's set that aside. Ultimately, someone else stop. Oh, it's power. We're almost done. So essentially, one of the things that was interesting is you look at Amazon App Store, which is a completely trustable app store. They do a lot of back-end work to make sure it's malware free and things like that. But if you want to put Amazon App Store on your non-Amazon device, which is certainly possible, they have a little Amazon App Store client. Step number 1, published by Amazon. Make sure you uncheck allow unknown sources. Why? Because for them to deliver apps, they're not Google, so the phone will reject it. So you've got to change the setting to even use Amazon on non-Amazon devices. If you start looking at MDM and MAM enterprise app stores and BYOD situations, all of those need you to change the setting so your enterprise can deliver you enterprise-based applications. We use an application called TestFlight, which is a completely legitimate application. Don't get me wrong, this is not doinking TestFlight, but it's just a situation where to use TestFlight, you get it from Google Play, and it allows you to distribute beta copies of your applications. To do that, you've got to basically check the unknown sources because TestFlight's got to install your apps. There are a compelling number of reasons and ways users encounter something where ultimately they need to change that setting. And just as much as the argument is users will never find the setting to undo it, even if they encounter situations that causes them to undo it, they will then never find the setting again to put it back. Right? So once it's undone, it's probably undone for life. And so there are very plausible reasons of why that number is not 0, and that many people kind of overlook. And that's not even counting the geographies that ultimately are not served by Google Play at all. So users have no choice but to go to third-party app stores. So kind of in closure, right? Sorry, I'm gating your lunch and stuff. So there's definitely, Blue Box is continuously kind of, working in this space and stuff. So you can kind of check our blog for updates, disclosures, posting this presentation stuff. That'll be coming in a few weeks. And I do want a little bit of a quick thank you to the Blue Box Android security team, Patrick, Felix, and Andrew, who certainly contributed through this big effort. And I do want to give props to the Google security team. For as much as the front end interaction, ultimately saying, here's a bug, go do something with it, there's a lot of behind the scenes work that ultimately has to happen to go coordinate all of these vendors, all of these carriers, and try to get that stuff out the door. Right? So from the perspective of all the people that I didn't see working behind the scenes of this bug to get it out there, whatever that definition is, ultimately I just at least want to say thank you and recognize that Google does do work here despite any popular opinion to the contrary. And apologies to some coworkers who happen to have the luck of the draw the same slot as me. So if you're in here, you're not in their talk, and that's a bummer for them, and I can't see their talk, and that's just the way it is. Yeah. So that's it. So thank you very much. Hopefully this was interesting.